when compilers were the AI that scared programmers. Do you know there was a thing? Hello, I'm Chris Thance. I'm a KMP developer. Tech Support said they're coming out Tuesday to close that portal up, and I'm like, okay, maybe we'll see. Today I'm going to be reviewing this video by Vivek Kaldar, which I give him a like and subscribe because this is awesome. A lot of people don't know we've had the AI revolution taking programmers' jobs since the 60s, 50s. And they went, oh my God, it's going to take over all the jobs. We'll just be able to go directly from the customer to the code and no problem. And everybody will be, all the problems will be solved. Let's see what's going on here.
The early history of high-level languages and compilers is fascinating. It is a tale of the pioneers of computer science, charting new territory, but also of deep resistance to new ways of doing old things. And I think it has a lot to teach us about how our tribe of programmers is wrestling right now with the idea of AI and LLMs writing code.
Yeah. It's like the lowest. It's like the thing. We still have to know what the code does. That's the other thing too. Is like this is all. There's this assumption that we all have the requirements that we all need to complete the program that we want and get the problem solved in the way we want it right from the jump. It's like, no, it's always been an iterative process. It's never been a direct line, and we have the dream, right? It's like, that's the dream. We can go directly from our imagination into implementation with no steps in between. It's like, no, there's always going to be steps, man.
In the early decades of computing, programming was done at the most granular level, hand coding in machine code or assembly language.
Yeah, well, it's the same thing, right? What's the difference? Machine code, assembly language, it's just mnemonics for the machine code. And those aren't two languages. It's this mnemonics for one thing. It's okay, let's keep going.
Painstaking work. Programmers had to manage operation codes and memory addresses directly.
Yeah. So C programmers do too. I mean, in a sort of way. An algebraic way as opposed to just the numbers. We're not using an algebra for the numbers. Okay, whatever.
One early pioneer likened to hand-to-hand combat with the machine. By the mid
hand-to-hand combat? Hand-to-hand combat with your own mind, maybe, to make this thing do something useful. To be able to break a problem down into the tiny little steps so a machine that's completely stupid and has no idea that it even is a machine can simulate this problem space that you've designed the machine to do. That's even possible. And people attempted all kinds of stuff that was just like, nope, that didn't work. Nope, that didn't work. We just know the things that did work. And we're like, oh, they were geniuses. It's like, no, all these guys just tried a bunch of shit they found, and we're just like throwing stuff at it with some insights, right? Some insights about which way to go. But they were like, they didn't know. If they knew, they would have done it right from the beginning, right? Let's keep going.
Mid-1950s, however, a revolutionary shift was underway. High-level languages and their compilers began to automate low-level details,
higher level. It's not high level. I know that like, oh, we got a high-level language, like higher level, higher than the bits and bytes and switches. Each one is a container of the previous one. Higher. Not high. Let's keep going.
Allowing programmers to write instructions in more human-readable forms. Developed at IBM by John Backus's team, Fortran was the first widely...
Yeah, that's the whole point, right? We found out early on, it's like, oh yeah, you can rig these things up to do all kinds of stuff. We can wire it together. Why even use software? Why not just use wire coding and make it to this permanent things? Like, well, that's not what we all want to do. We want to do something different. It's like that, but we want this thing over here to change, or this needs to be different, or we're doing it different this way, or we found a new way to do it. Now we got to do this whole other way, or this new machine's available. We want to use that instead of this other one. It's never just a one shot. It was like there's this dream like, oh yeah, I just implement it, go, and it's like, well, that's part of the problem is getting it up, right? But then getting up and running it and then passing it on to somebody else because you don't want to manage this for the rest of your life. So all you want to do is this one thing. Some people do. I get it. Some people want to run that tractor. That's the only thing. Their first tractor is the only tractor they ever want to run. Like, I get that. They only want to plant corn. They only want to run that tractor. They don't want to do anything else. I get it. But I'm not that kind of, but most people aren't that kind of person. So it's always going to be changing the tractor, modifying the tractor. Are we doing lawn mowing? Are we doing wheat? Are we doing corn? You know,
used high-level language. It enabled scientists and engineers to write formulas and algorithms in a more natural mathematical notation, which the compiler would then convert to machine instructions. Fortran dramatically reduced the number of statements required. A program that might have...
Right, instead of using machine language to simulate these things. Yeah, you had somebody that went through all the loops to do, and all the translations, the sine, cosine, lookup tables, and adding floating point numbers, all that stuff that you'd have to do by hand before, or already know how to do it by looking at somebody else's how they did it. And you don't do that stuff anymore. Yes, it sped that up, of course. Yeah, but you still don't know what the math does. What problem are you solving? Are you got the units right? How would you know? Can you? There we go.
Needed 1,000 assembly instructions could now be done in about 50 Fortran statements. The Fortran compiler quickly proved that compiled code could approach the efficiency of hand-coded assembly.
Yes, of course, because you're going to be doing assembly already. So the assembly language is always tied to the damn machine. So it's not portable. So you got to get really good at the assembly language for that machine. Not only the mathematics and the formula and the problem space, and the solution space. So yes, there was only a certain number of people that could even do that. So yes, by cutting that part out, which is always redundant, the same damn thing. It's a library. Yes, you're going to speed up the process. I mean, it wasn't Fortran did. It's like this whole concept of putting complexity behind boxes. You know, have inputs and give the outputs. I don't care how the thing works inside. Just I have the input, give me the output. I'm working on this other thing. I'm not trying to learn how to run a compiler.
Early skeptics who insisted that high-level code could never be as efficient as handcrafted machine code were confounded when Backus's team delivered an optimizing compiler that made Fortran programs run nearly as fast as assembly. Adoption was rapid.
Yes, of course. That's going to be inevitable. And anybody that said that, oh, it wouldn't be the same, it's like, guys, you're never going to get the same, but you're going to write the whole thing in assembly just to get 0.01% better. Come on, this is ridiculous. It was ridiculous at the time, and it was foolish to even think this way, but people have thought this way.
1958 survey found that over half of all code being run on IBM computers was generated by the Fortran compiler.
Yes,
this was a stunning validation of this new approach.
Why is it not stunning? It makes sense. If you can write a program, instead of taking 50 hours, it takes 3. Or 75 hours full of all kinds of bugs. It doesn't even get to completion because you got all kinds of problems you can't figure out. Your floating points, the numbers are off because you didn't know some sort of implementation detail inside the assembly language that had to do with special bit flipping thing, all that stuff. Of course, it's going to be better. It's a stunning achievement. Come on.
Even then, many working programmers were skeptical or resistant. They had deep expertise in assembly language and were proud of the arcane skills needed to wring efficiency out of early machines.
Yes,
John Backus later described this culture as a priesthood of programming. In the 1950s, programmers often regarded themselves.
Yes, the ivory tower was alive and well. And that's why this ivory tower stuff, the closed source, all that junk. It's silly. It doesn't last very long. Eventually, someone gets out. Someone's like, "No, we're not doing ivory towers. This is ridiculous." And the information gets out and it gets spread around. So the initial approach to the ivory towering thing, yes, it took them a hard time to write the compiler. Yes, to figure out in assembly language how to do floating point addition and sine cosine efficiently. Yes, it took a long time to do that. Yes, and they deserve credit for that. But now you put it into a library and you're saying I have to understand and appreciate all the things you did all the time. It's like, come on, we can't even. That's not how the humanity works, man. Once we have a gasoline engine, we hook it up to all kinds of stuff. But getting the gasoline engine going was a pain in the dick. Figuring out that just getting gasoline going was a pain in the dick. But getting all that stuff together, yes, it was hard to do. But we don't really think about that anymore. We just want to drive from here to here.
As guardians of arcane knowledge, possessing skills and knowledge of mysteries far too complex for ordinary mortals.
Yes, it was ridiculous. Yes, it is complicated to get the binary machine to run a floating point arithmetic. Yes, it's hard. It's like a particular model of particular compiler with that particular architecture, with that particular instruction set. Yes, very arcane, very esoteric, and totally goofy, and was going to go away anyway. Sort of like knowing which kind of screw and nut to make an engine, and you tuned it up, this engine, for this particular purpose. Yes, that takes skill and all the precision parts and milling it yourself and all that stuff. Yeah, making an engine is impressive. But if we can make a machine that makes engines, then I don't want to know all those details.
One of the most frequent arguments against compilers was that compiled code could not be as efficient or compact.
True. Using static variables in C and C++ is faster to access as opposed to going through an API. Yes, you are correct. But it's not you can't extend it. And if you try and get other people involved and want to look over the code that your genius code that you've written with all your esoteric stuff and no comments, oh yeah, you're gonna have really good job security until you get obsoleted by someone who goes, no, I can just do a library up. I can just look at your code and put it behind a library and then write it in C, so it's now portable and doesn't even need to have their same language, but it's less efficient. Yes, true. But now my code is running on 8 platforms, while yours is running on one very efficiently. That just went obsolete because the company's no longer running that chipset anymore. Yes, you're the most efficient on that old chipset for that one platform, but I've got it now on 22 platforms running that same code, same ideas, same everything, but 0.1% less efficient. Yes, because I'm using compilers to get this code, but I'm now running. So the says this is the I can't, this is, let's keep going.
As handwritten assembly. People would say they could be more efficient in assembly, giving a whole litany of reasons to avoid high-level languages.
Absolutely 100%. It will be 0.1% more efficient at the cost of what? No one understanding and being left behind in the dust because no one supports that chipset anymore and nobody cares because we're using compilers now.
And this was not entirely untrue. The earliest compilers sometimes did produce.
So he's actually true and he's wrong, right? He is factually correct and wrong. I mean, he can be, just because his statement is true doesn't mean he's right. It means his statement is true and he's wrong.
verbose or suboptimal machine language. A 1965 Honeywell management briefing noted candidly that a highly skilled assembly programmer could still beat COBOL's output in efficiency. But
true, it also, buddy. And how many of those are you going to replicate? One guy or 55 compilers that get you 95% of the way there? And now we're running on all these platforms and we just put it in the cost of production, as opposed to try to replicate that one super genius. I can't. It was surprising that these conversations go on, but this is we can link it into today with the LLMs. Can we link it into today? We can link it in. We can link it in. Let's keep going.
Questioned how many highly skilled programmers are available or even needed at the average installation. In practice, compiler optimizations improved quickly. IBM's Fortran team introduced the first optimizing compiler and proved that compiled code could approach or match the performance of hand-coded assembly in many cases. As these successes became evident, the purely performance-based objections began to wane. The next argument was control. Many assembly programmers were accustomed to having intimate control over memory and CPU instructions. Surrendering this control to a compiler felt...
Well, they had to. What was the option? What was the alternative? There was no alternative. You had to do it. So yeah, you better like it. You better love it. Because if you don't love it, you're gonna be like, fuck this. I'm out. And you're not gonna be a programmer anymore, because that's what programmers were. They were assembly language. That's what you did. Let's keep going. And you were tied to a machine and a corporate. That means you like this whole vendor lock-in they complain about. Oh yeah. The assembly language is the first vendor lock-in.
There was a sentiment of, if I don't code it down to the metal, how can I trust what's happening? In some cases...
Yes, you're absolutely correct. How can you trust what's happening? Well, maybe you could test the compiler's output and see if it does the same stuff. Yeah, if you're doing systems level stuff that you have to get down to the machine, down to the hardware, yeah, of course. Input, output, yes. So specific new peripheral, yeah. You got to get down. You might have to do assembly language. Try to avoid it, but you might want to. You might need to back then for sure. But today, well, I mean, why would you want to for sign and cosign? We're not gonna hand assemble that. What are you, out of your mind? No.
It was about efficiency. In other cases, it was about debuggability and understanding programming behavior. However, as compilers matured, they began providing diagnostic output and listings that actually improved understanding.
Yeah.
There was an implicit fear that making programming easier might reduce the prestige or necessity of the seasoned programmer. High-level languages opened the door.
Even back then, this is back in the 60s. Oh my God, if we make it so assembly language isn't so freaking hard to do and you don't have the vendor tie-in, we might lose programmers. And it's like, explodes number of programmers.
For newcomers to write code without years of experience in binary or assembly. The priesthood culture Bacchus described suggests that some experts guarded this domain closely. Yes. Grace Hopper encountered this attitude when promoting compilers.
Right. She's the first one to expose this. That's why I do appreciate Grace for exposing this priesthood, and they were keeping these computer stuff for themselves. And they definitely cut it off. They cut off access to people that probably could have benefited we'd probably be 10 years ahead by now if we didn't have this priesthood attitude that comes directly from academia. Mathematics, science departments had this attitude. Oh, we're better than, you have to come in, you have to know all the language and lingo. From how are we going to learn it? Well, you got to be part of the department of academia. It's like, oh, so you just have white ivory tower priesthood. Oh, okay, well that deserves to be toppled.
Management and colleagues initially thought the idea of automatic programming was crazy, fearing it would make programmers obsolete. Hopper and others had to repeatedly demonstrate that these tools would augment programmers' productivity, not replace the need for skilled people. In fact, far from eliminating jobs, high-level languages led to an explosion in demand for programmers. High-level languages opened
and they all fought it at the time, like, no, it won't happen. It's like, well, you're going to lose some of your control. You're going to give up, 90% of your control, but you're going to gain 10,000 more programmers who are going to do all kinds of stuff that you haven't even dreamed about. You damn gatekeeper.
Door for many more
They're
people
so
to become
bad.
programmers.
It's so
In the
bad.
1940s and early 50s, programming was the domain
It
of a
never
small
changes
elite
either.
with specialized
Same
training,
shit.
often in mathematics or electrical engineering. By the 1960s, that pool had widened significantly. Fortran had allowed scientists and engineers to directly write programs for their problems, and COBOL did.
I first wrote my first Fortran program. I was helping this lady out because I was, I don't know, 12, 13. I just got my own TRS-80 basic computer, and she was using. She gave me her textbooks on Fortran. I read over it and helped her with her homework. She was in college at the time. She was in a college course, and then she let me log into the college and look at her course and play around with the Fortran compiler and stuff. So I was like, was it 1981, 82, something like that?
Something similar for business. It enabled individuals with domain expertise, such as in accounting or inventory, to learn programming without needing a deep computer science background. As one retrospective put it,
especially with like accounting, where you're just taking things from one place to another, basically a bunch of spreadsheets. COBOL was like the original spreadsheet type of thing. It was very limited, but for what people wanted to do with it, it's like that's a lot of the computers were doing stuff. This COBOL stuff is like basic adding up long lines of numbers and then subtracting long lines of numbers and reconciling all that stuff. All that kind of stuff was what the computers were. The Fortran, the scientific stuff, was sort of like a side venture. The main line was always the COBOL. That's why it was shocking that the assembly language people didn't understand, like, the main line isn't this scientific shit. It was this business accounting trying to deal with all these checks coming through and reconciling all the records with all this bank stuff. Let's keep going.
COBOL democratized coding. Companies could take everyday people and train them to be useful COBOL programmers in a few months, allowing a new influx of talent.
Well, for that particular narrow domain space, it's not like COBOL was doing the scientific, all this NASA to the moon shit. They were just doing accounting, which was just as big a problem. There's so many. There was such a push to get this through because they're drowning. Right, they weren't able to keep up with it, and it was limiting their economic engine. So they had to find something. And Grace Hopper, if it wasn't for Grace, we'd still be trying to do it in the assembly language for way too long. She got such pushback for doing COBOL.
Into the field. The result was a dramatic expansion of the programmer workforce. The role was now seen as more akin to logical clerical work rather than electrical engineering. This set the stage for programming to become a mainstream profession rather than a niche craft.
Correct.
As compilers automated the gritty aspects of coding, the skill set for programmers evolved. There was less need to memorize machine instruction sets or calculate memory addresses by hand, tasks the compiler would handle flawlessly. Instead,
let the machine do that stuff. Ugh, why do you even want to do that in the first place? Yes, it's raw down to the metal. Yeah, it was how the original computers all had to work. What else was there? No, that should all have been refactored. It was going to happen anyway. So it was like, it was just a natural evolutionary step.
Shifted to problem analysis and program design. This is reflected in the terminology. The rise of the term analyst in job titles during the 1960s. A high-level language freed programmers to think more about what the program should accomplish rather than how at the bit level to implement it. One manager in 1963 noted that with the advent of COBOL, he valued employees who understood the business logic and could structure a program clearly. The compiler would take care of the low-level details if the high-level logic was sound.
In a domain space, right? In a specific domain, so COBOL is perfect for this purpose because it was basically spreadsheets. So before spreadsheets were a thing.
In short, the introduction of high-level languages elevated the abstraction level at which programmers operated. By making programming more efficient and accessible, high-level languages enabled many more applications to be developed in a given time. Businesses could automate more of their operations, which in turn drove demand for more computers. This expanded the scope of automation in society. Entire new domains for computing emerged because software could be written fast enough to respond to business needs. High-level languages were the catalyst that helped move computing from...
If it wasn't for the high-level languages, we'd still be stuck with this really arcane shit. But again, it was a matter of time because they were already implementing subroutines in assembly language, and that was just like, once that happened, it was inevitable that we'd be switching over to, because every subroutine has a name. It would be named, right? We'd give it a name, right? But so that was just the next step over to like the high level stuff. It was just the naming of the subroutines. That was sort of like the next flavor. Let's keep going.
From a limited experimental phase into a major industry of its own. The shift from assembly language to high-level languages with compilers in the 1950s and 1960s has striking parallels to today's transition.
Yeah, it's always, this cycles happen so many times. It's just always the same thing.
Coding to AI-assisted programming with tools like GitHub, Copilot, Cursor, Aider, and others. In both cases, a fundamental change in how code is written is occurring, leading to initial skepticism, gradual adoption, and ultimately
overhype. But we have to go through the overhype phase. Now, COBOL, I don't know if there was an overhype phase. There might have been because they put it everywhere, and it's like they didn't think about the extensibility. They just thought the writing of it, right? Just getting the code to run was a big deal. So they didn't think about the extensibility. So there's these other problems, these tag-on problems that happen that aren't seen from fixing the first problem that they're trying to address. There was so COBOL. I guess the backlash of COBOL is happening now, where there's nobody that knows how to fix any of this stuff. And people talking about getting rid of the IRS and things like that. And it's like there might be a reason that's not just political. It might be they can't update the computers anymore. People are dying and they can't find them anymore to fix the stuff. So it'd be easier to revamp and start over from scratch using modern technology than to train convert over the old COBOL systems. So let's go.
Read definition of what it means to be a programmer. The debate playing out today about what it means to be a programmer when LLMs can churn out large amounts of working code is of exactly the same shape. Let's learn from it and not make the same mistake.
Well, I mean, we're going to make the same mistake. We have to. That's how we learn. We have to learn everything the hard way. All right, well, give me a like and subscribe, and go over there, and I'll leave the daily do in here and give him a like and subscribe, and we'll talk to you soon.